Okay, we're going to take a look at the fundamental fact of fraction pairs. And actually we can abbreviate that as FFFP. That's what we're going to abbreviate it as. So we've talked about a definition of fraction and the theorem of equivalent fractions. So from those two, now we can say two fractions may be compared by using equivalent fractions to make fractions with the same denominator. Okay, so that's a huge next step. So for example, if we have 4/3 and 9/7, then what we can do is with 4/3 we can pick a constant c that is going to give me the same denominator here. Well, what would make sense is to make 7 our constant. So if I multiply both sides by 7, or both top and bottom by 7, I get 28 over 21. And the same thing over here with 9/7. If I have 9/7, then to get a common denominator, it would be to multiply by a constant of 3, both the top and the bottom. And that is going to give me 27/21. So essentially I've taken a fraction, made an equivalent fraction, a different fraction, made an equivalent fraction, but now these fractions can be compared because the denominators are the same. All right, so let's try that with a number line for 1/3 and 2/5. So draw a number line. Alright, so if we start with, and we're going to make this kind of big, so here is 0, and since these are going to be less than 1 anyways, let's just make this 1, just to make it easy. So 1/3 would mean that I have to split this into 3 equal, or partition this into 3 equal parts. So here is 1/3 and 2/3. Okay, and let's do another number line. Make it the same length, and we're going to use the same unit, so we'll just make this 1. But now this is partitioned into fifths, so we're going to turn this into, split it into 5 equal parts. Okay, and this would be 1/5, and this would be 2/5, and 3/5, and 4/5. All right, so what would be a partition that would give us the same denominator? Well, here is 1/3 right here, and 2/5. So if we do this, that would mean that we would have to do 5. Remember, yes, we can visually see that 2/5 is more than 1/3, but we need to prove it. So we're going to take this and partition it into 5 equal pieces. 1, 2, 3, 4. So that gives us our 5 partitions. And we do that again and again. So remember now, between 0 and 1, this has been partitioned 15 times. So this would be 1/15, 2, 3, 4, and this would be 5/15 right here. Now if I have partitions of 5 already and I want to get to 15ths, then I need to partition each one of these segments into 3s. So this would be, split this into 2, split this into 2, or it's actually 3, but I'm marking it twice. Okay, split, or partition. Alright, so again, this would be 1/15. And notice that even when I draw this, I've used the same number line, these are starting to match up. So this would be 1/15, 2/15, 3/15, 4/15, 5/15, and where 2/15 is, this is 6/15. So now we have them on equal footing because our partitions are 15, and we can see that 6/15 is greater than 5/15. Okay? We could see it visually, but now we've got actual proof. Because the denominators are the same, we can compare the numerators and find out for sure that 6/15 is greater than 5/15. So what this leads to is a fundamental fact of fraction pairs. So go ahead and copy this down. And basically it just proves what we talked about at the top. Any two fractions can be denoted by fraction symbols which have the same denominator. So this is the key point in the FFFP. So if we want to make a general statement about that, if given fractions are k over L and m over n, where k, l, m, and n are any whole numbers, then k times a constant, which in this case our constant we used was the denominator of the other fraction. So k times n and l times n, and that means that if we take the denominator from the first fraction and use that as our constant, l times m and L times n. Notice what are the same. Right here, I'll just draw a dotted line. L times n is going to be the same as L times n. That's where you get your same denominator. Okay, let's go over the again for why this is true. So let's just write it out one at a time. Again, if we have k, a fraction that we're going to call k over L, and we have another fraction, again with different whole numbers, but we're going to call it m over n. Remember that by equivalent fractions, we can multiply using a constant, and in this case we're going to use n. We're going to use the denominator from the second fraction. So we can say this because of equivalent fractions. This is the theorem of equivalent fractions. All right, well then the same thing is true here. We can take mn and we can multiply it by a constant. In this case, we're going to pick that, you're going to choose that constant to be L. So we're going to say multiply top and bottom by L. And this is where you get that same denominator. Now, granted, in this example, they are turned around, but L times n is the same as n times L, and that's where you get your same denominator. So again, this is because of the theorem of equivalent fractions. And because we can say that, that means that these are already equal, which means this needs to be equivalent, and because they have the same denominator, now we know at the top, we can compare the tops. All right? So FFFP is not the only way to compare fractions by putting fractions on equal footing. Equal footing just means with the same denominator again. All right? So we are able to compare them. So let's consider 3/4 and 1/6. Okay, what other equivalent fractions can you make other than 18/24 and 4/24? And you can see that this was gotten by multiplying 3/4 by 6, both top and bottom, using 6 as the constant, and multiplying 1/6 by 4 to get 4/24. You should be able to see that there might be an easier way to get a common denominator here. And that would be, if we were to work this out, you can pause the video and see if you want to try this, but What is another common denominator here without going all the way to 24? Well, you could use 12. So you could pick a different constant and come up with 12. In this case, 3/4. If you multiply that by 3, you get 9/12. And if you take 1/6 and multiply it by a constant of 2, then you get 2/12. Okay? So now you can compare these two, but we didn't actually use, we did use a constant, but it wasn't the same, it wasn't that we were multiplying by a constant of the denominator. So to finish up, what are some uses for the FFFP? So how can we use common denominators? What would that be useful for? So take a second to think about that and then write down what your prediction is, and then we'll go over it real quick. All right, well, we can take, if we know we have a common denominator, we can actually compare, so we can tell which fraction is bigger than the other. So a use of FFFP is to compare fractions. We can also, what would this also be used for? Well, when we add fractions, we can't add unless we have common denominators. So adding, and remember, subtraction is the opposite of addition. So add and subtract fractions. So you can see where we're going with this, add and subtraction of fractions. You can see where we're going with this as to what we're going to be talking about next is eventually we will get to addition of fractions, and FFFP will be part of the proof of why we can do that. All right, see you in class.